Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 42. Now in the previous lecture, that is lecture 41, we had started our discussion about the interaction of light with matter, and I had told you how connecting absorption, spontaneous emission and stimulated emission would give rise to very powerful ideas, right, to understand the intensities of spectral lines. Okay, now as part of it, we started our discussion with absorption. I kept the same content from last class for convenience. And we discussed the idea that, the rate of absorption of electrons, right, from the ground state, that is dN1 by dt, could be connected as the negative of the rate of the change in the number of electrons in the excited state. Okay, right? I'll clarify. The rate of change, right, in the number of electrons from the ground state is equal in magnitude and opposite in sign of the rate of change of the number of electrons in the excited states, where N1 is the number of electrons in the ground state and N2 is the number of electrons in the excited state. Please note one point. I did not clarify this in the previous lecture. Now I'll make it very clear that, this expression is meaningful, right? And we can compare the number of electrons in the grounded excited states, right? If only, initially the excited state is unpopulated. Okay, right? Because I'm using the symbol N2 here, and the same symbol N2 is also used here, right? So mathematically, for this statement to make sense, initially there are no electrons in excited state, right? And it's only after that some absorption happens that some electrons from the ground state they get populated in the excited state. Are we clear? So what I did not tell you in the last class, I had simply given you that N1 and N2 are the number of electrons in the ground state and excited states respectively. But what I did not tell you was that the excited state is initially unpopulated. That's a very logical and meaningful starting point, because you would expect all the electrons to lie in the ground state a priori. Okay, right? It's only after interaction with light that some electrons get excited and they go to the excited state. Now under this framework, we have absolutely no problem with this particular statement, right? And so therefore, all the electrons N2 that are in the excited state come only from the ground state. And that is why we have this expression here, whose magnitudes can be equated. And of course, because the direction is different, if I'm going to call this as positive, that is dN2 by dt, right, as a positive number, because it's opposite in direction, this is going to be the negative 1 times dN1 by dt. Are we clear? Okay. So the important points to understand here are how the N1 and N2 come up. N1 and N2 come up because of a transition from the ground state to excited state, right? N1 is the number of electrons in the ground state and N2 in excited state, which happens as a result of excitation from ground state to excited state. Okay, right? Initially, the excited state is unpopulated, point number 1. And point number 2 is that we have a change in sign here. These expressions are equal because we want to uniquely define a rate. And to uniquely define a rate, I should have a negative sign in front. Okay, the negative sign indicates that, see, if N2 minus N1, right, is positive, right, then N1 minus N2 is going to be negative. So having a negative sign before it makes sure that mathematically this expression is meaningful and unique. Are we clear? And then it's a negative sign to just indicate the opposite direction. That is N2 by d in the left hand side. That is dN2 by dt. Right? We have the excited state to ground state transition happening, whereas over here, right, we're talking about a ground state to excited state transition. For our understanding, okay? Is it clear? In absorption, of course, electrons always move only from the ground state to the excited state. Okay. However, it can also be expressed in terms of the change of electrons, right, in the excited state, right, such that all those electrons are coming only from the ground state overall. Fine. Okay. Yeah. Okay. So now we completely understand these two terms and also the negative sign here. Okay. I'm going to call this expression A. Now this is for absorption. Now similarly, right, notice that some electrons, right, some electrons may be getting absorbed. Okay. Now after absorption, what did we discuss is going to happen next? The next thing that is going to happen is what is called as spontaneous emission, which we had abbreviated using the notation SPONT in the previous lecture. Okay, right? Now as part of spontaneous emission also, right? Now let me say that N2 electrons, right? N2 electrons are spontaneously emitted from the excited state to the ground state. And this is therefore, right? This is therefore going to be the negative of, this is SPONT, and this is also SPONT. Right? Is this expression clear? Having spent so much time with this expression, right? It naturally follows that for spontaneous emission also, a similar expression should be true. In other words, the number of electrons from the excited state which fall back to the ground state as a result of spontaneous emission, right, is going to be the negative of the number of the electrons which are involved in the ground state, right, which are coming from this. Are we good, right? So this is for spontaneous emission. And now it's going to be very clear that even for stimulated emission, the electrons that are going to be in the excited state, right, as part of stimulated emission are going to change such that this expression holds good. Right? So notice therefore that the total number of electrons in the ground state is N1 and in the excited state is N2, such that all the electrons are coming only from the ground state. Okay, all these N2 electrons are coming only from the ground state. In other words, right, the upper bound N2, right, N2, the max value it can reach is N1. Okay, right? And because both N2 and N1 are positive numbers, my N2 is always less than or equal to N1. Always, right? This is just to, mathematically make sure that everything that we're talking about is completely meaningful. Let me call this expression like spontaneous, SP for spontaneous and SC for stimulated emission. Okay. Now I shall retain both this equation that is written in page 1, the absorption equation, the spontaneous equation and the stimulated equation. All right. Now, if you consider this expression, this expression A, that is like the expression for absorption. Now, what are the factors? Okay, what are the factors does this depend on? That is, if you consider either the LHS or the RHS in A, right? Now, you can think that the LHS or RHS are of course going to depend on N1, that is the number of electrons present in the ground state, right? Because the electrons present in the ground state are what are eventually going to be going to the excited state. Okay, right? So therefore, in A, this rate of absorption is going to depend on the number of electrons. Okay, not just that. Okay, not just that. Now, therefore, I'm just going to say that your LHS is equal to RHS, right? In A, right? Is going to have a dependence. I'll tell you how I write this term later, but I'm going to start off with the dependence part. It's going to depend on the number of electrons. Okay, right? And not just that. What Einstein, told was, it not just depends on the number of electrons, it also depends on the energy density factor. Recall from black body radiation. Just a small digression, I'll write it here. From black body radiation, right? We're going to have something like the spectral density, right? Which we saw in the tutorial, I think. Such as the expression, I'm going to call it U. Okay, I'm going to call this U, right? as going to be h nu cube, right? H nu cube by c cube times 8 pi times 1 over e to the power kbt e to the power h nu by kbt minus 1. The minus 1 is in the denominator. I mean, as part of the e and not as part of the exponent. Okay, I'll again tell what I've written here, because I've written it in reasonably small font. This is u, right? Now this is coming from the black body radiation, and we saw in the tutorial, right, that Planck's expression for the black body radiation is given by h nu cube by c cube times 8 pi times 1 over e to the power h nu by kbt minus 1. Okay, where all terms have their usual meaning as we discussed in the tutorial. The point to note in this expression is the units of u are going to be joule per meter cube, right? Joule per meter cube, and I think there is also going to be 1 second, yeah, right? So it's going to be joule per meter cube times the second factor. Okay, clear? So this is h nu cube by c cube. This is all dimensionless, and h nu cube by c cube, h is going to be joule second, and this is going to be per second cube. And because from the frequency term, the per second cube, and then from the c cube, the per second cube will be vanishing, and the h is going to have a joule second. So that the joule second and then per meter cube from here. Okay, so this quantity, okay, right, is what is called as u. Now Einstein, okay, right, what is this u? It is a measure of the energy density, right? The energy, it's conventionally called the energy density per bandwidth. Okay, right? Now, so Einstein assumed that at any given point in time, now because this is a kind of a measure of energy density, assuming the black body radiation model is valid, okay, assuming that the black body radiation model is valid, so assuming the black body model holds good, even when an atom is absorbing light, even absorbs light. Okay, so what Einstein said was that this rate, okay, is of course dependent on the number of electrons, and not just that, assuming the black body radiation model is going to be good, right? He hypothesized or postulated that, okay, it should also be dependent on this term u. It should be dependent on this term u, right, which is given by the Planck body expression, right, which is given by the Planck body expression u. And okay, so it should depend on these two things. So there should also be some kind of a proportionality constant, and let's just call that B12. Okay, right? Are we all good? So so how did this term come up? This term came up by the intuition that the rate of absorption should depend on the number of electrons present in the ground state, because it's the electrons in the ground state that are getting excited. Okay, so therefore this term comes up. How did this term come up? Well, this term came up based on Einstein's idea that the black body radiation model, that is, when this atom absorbs light, it absorbs similar to what a black body does. Okay, right? So under that assumption, because the energy density is given by this particular factor, Einstein said that, okay, let us also take this u here, that the rate of absorption is also depending on the energy density. Okay, right? Energy, strictly speaking, it is energy density, times there is also a second unit here, okay, time unit here, okay, right? He said it is also proportional to that. Now, having introduced two terms to consider the proportionality into equality, he had this constant which is called as B12, right? This is what is called as one of Einstein's coefficients. Okay, now the units, because the units of u and the units of n1, the units of B12 can be appropriately calculated. Are we fine? Okay, in other words, it's going to be the unit of B12 is going to be the per electron, right, and per this, that is like per u unit. Okay, that's all there is to it. Are we clear? And are we clear as to how exactly we obtained it? And notice that, this is not an exact mathematical equation in the sense that there were no physical assumptions involved in the formation of this. Okay, it is not a exact mathematical equation in that sense. What's happening is, hey, we have to we need to bring about the connection between the various terms, right? Spontaneous emission, stimulated emission, and absorption, etc., etc. For this, Einstein used a clever idea that the rate of absorption should be dependent on the number of electrons in the ground state, right? And it also should be dependent on the U factor from black body radiation, and therefore the proportionality constant is just B12. That's it. So here's a beautiful equation that we obtain, a beautiful simple equation we obtain based on applying physical intuition, right, to a mathematical equation. Are we good, right? That's it. Okay. So this is from equation A. I'm just going to call this equation A prime. Now, similarly, if you look at, the spontaneous emission in SP, right? In spontaneous emission, what we note is that the LHS is equal to RHS. That is this term, the term containing the number of electrons in the excited state and the term containing the number of electrons in the ground state, right? Now, they are actually equal to minus A. Let's say that A is some constant, and it should, I'm going to call this 2, 1. Okay, see, when I was using the absorption notation, I use 1, 2 to indicate that absorption means going from a ground state to excited state. That was how we showed our equation, right, earlier. So therefore, this is going to be B12. But because it's emission, right, because it's emission, and because it is spontaneous emission, there is no dependence on, any U factor, etc., etc. It is just going to be some constant, right? It is going to be some constant times, what would you guess? The number of electrons in the excited state or the ground state? It is going to be the number of electrons in the excited state. Now, do you all understand why there is no U term here when we consider the spontaneous emission? It is because the U term arises only when there is, a photon to be absorbed. Okay. As part of the spontaneous emission process, there is no photon. Absorbed. Okay, right? A photon may be emitted. Okay, but no photon is absorbed. So therefore, the rate of spontaneous emission only depends on the number of electrons in the excited state, because emission is starting from the excited state. Okay, right? And therefore, some coefficient is going to be A21. But why this negative sign here? Because we're just following the same convention we are using throughout. That is, for absorption, whenever we consider a change of electrons from excited state to ground state, that is Dn2, we are not putting a negative sign here. Okay. Similarly, in the case of spontaneous emission also, we're not putting a negative sign in the LHS. Likewise, here also we don't put. However, whenever, we consider a rate of change of electrons, right, as part of the ground state, that is in the RHS, we have a negative sign. Okay, right? We have a negative sign. And so overall, what does it indicate? It tells us that absorption and emission are happening in opposite directions. What do I mean by opposite direction? From excited state to ground state versus ground state to excited state. So therefore, by the same analogy, okay, by the same analogy and idea, here, if I do not have a negative sign in front of my equation corresponding to absorption, right, for emission, to indicate, to indicate clearly and to not miss the direction, I have a negative sign over here. Are we all good? Okay, right? So the negative sign here arises to distinguish between absorption and emission in short. Okay, right? Okay. So we've considered absorption and spontaneous emission. Let us now consider stimulated emission. In STIM, right, that is, I'm talking about this equation, your LHS is also equal to your RHS, which is equal to, what is the first thing you should see based on this? The first thing is to get a negative sign. Why a negative sign? Because emission involves, emission. The minute I'm talking about emission here, it's the opposite sign of absorption. So therefore, I should have the negative sign here. Now, after having the negative sign, okay, the next thing is going to be, of course, it's going to depend on the number of electrons. So I'll put the N2 because it is the number of electrons in the excited state that are going down to the ground state. It's N2 and not N1 here, right? That is said. Now, in stimulated emission, recall what is stimulated emission from the last lecture. It involves the transition from the excited state to the ground state when a photon hits the excited state, right? In other words, there is therefore going to be a U dependence here. For the same reason that there was a U dependence as postulated by Einstein, right? We're going to have a U dependence here also. Now, again, this is not an equation that holds good in the absence of any physical assumption, okay? But the moment we make a physical assumption, then this expression, that is, that there is going to be a U dependence based on the black body radiation, is going to be consistent with what we saw here, okay, right? So we have a negative sign, we have a U, and what is left to be included? It is the proportionality constant. So the proportionality constant, I am now going to be indicating this as B21. Why B21 and not B12? Because 12 refers to absorption, that is ground state to excited state. But when I'm talking about 21, it is the excited state to ground state. Are we all good? So therefore, we now have three equations. Okay, right? We now have three equations. One equation for the spontaneous emission, one for absorption, and one for stimulated emission. And all of these could be related with what are called as the Einstein coefficients. Your B12, A21, and B21 are all called as the Einstein coefficients. Okay, right? And by assuming black body radiation, you could also invoke the black body model within this. Okay, but what did we do so far? We simply wrote down a bunch of expressions after making some physical assumptions. We did not really bring about any connection between these three. Okay, let's do that now. So from these expressions, okay, from your A dash, and I'm going to call this like SP dash, and this is going to be STIM dash, right? Okay, right? So from these three expressions, A dash, SP dash, and STIM dash, and also, considering your expressions A, SP, and STIM, that is absorption, spontaneous emission, and stimulated emission, we see that net dN2 by dt. In other words, right, the net dN2 by dt, the net rate of change of electrons from the excited state, is given by, your dN2 by dt as part of absorption plus your dN2 by dt as part of your spontaneous emission plus your dN2 by dt as part of your stimulated emission. I mean, that's the net rate of dN2 by dt, right? Likewise, we can also have an expression for dN1 by dt, which is going to be the sum of all of these two terms. Okay, are we all good? All right. So now that we have this expression, and recall from expressions A dash, SP dash, and STIM dash, all of these terms, right? All of these terms can be expressed in terms of the Einstein coefficient and also be connected with the black body radiation. So therefore, this is also equal to, so this implies, okay, right? This expression implies that your dN2 by dt is also equal to the sum of these three terms, that is N1U B12, right, minus A21N2 minus N2U B21, right? I'm just substituting whatever we wrote here in terms of black body radiation and number of electrons for the total number of changing electrons in the excited state. Are we good with this? Okay. So now we have this expression. Let us call this, this is going to be expression, we've used what? Absorption, P stim, etc., etc. Let us just call this expression on page 5. So I'm just going to call this expression 5. Pardon the randomness, okay, right? I thought of the equation naming scheme is rather arbitrary, but there is at least some logic. The logic is that because this is on page 5, This is expression 5. Okay, right? So I no longer need this part also now. So I'll delete it. See, so we have the expression for dN2 by dt, the net change in the number of electrons, per any given unit of time, expressed in terms of the number of electrons in the ground state, the number of electrons in the excited state, right? And also the Einstein coefficients under the assumption that the black body radiation holds good. Okay, right? This is the meaning of this expression 5 here. Okay, now under net thermal equilibrium, I'm going to introduce one more term. Under net thermal, right? Under net thermal equilibrium, that is, when the rate of electrons defined as dN2 by dt, right, as negative dN1 by dt is equal to 0. In other words, the system is never far away. It's not that all the electrons are in the excited state or all the electrons are in the ground state. There is going to be a reasonable population in both the ground state and excited state. Okay, when will that happen? When it will happen when the net rate, okay, right, when the net rate is going to be 0. In other words, whatever electrons go up from the ground state are also again going to come back in time, so that this flux, this constant flux, is always maintained. Okay, this is what is called as the thermal equilibrium condition, right? So under this condition, what do we see? dN2 by dt is equal to negative dN1 by dt is equal to 0, which means that from expression 5 here, this is also going to be 0. Are we good, right? In other words, right, your expression 5, it changes to, we get from expression 5, B12 N1U, right, minus B21 N2U, which is equal to A21 N2. I'm going to call this the expression on page 6. So this is expression 6, right? So under thermal equilibrium, we get this expression. Okay, this is going to be page number 7. Okay, now from this, right, I can therefore get an expression for U, right? I can get an expression for U. Okay, so from page 6, I get an expression for U such that my U equals A21 divided by N1 by N2. Okay, right? N1 by N2 times B12 minus B21. How do I get this? How did I get this expression? I take U as common, and then I put the rest of the things in the denominator, and after that I divide throughout by N2. Okay, I divide throughout by N2 and I get this expression. All right, are we all good? Okay, so we have derived some expression for U based on the idea that there is going to be net thermal equilibrium. Okay, right? So I'll actually stop this lecture with this at this juncture. I'm just going to call this expression U, right? U to end it. Okay, right? So this is expression U, wherein under thermal equilibrium, we understood that assuming the black body radiation holds good, right? And also by equating the idea that your net rate of change of electrons is going to be the sum of all the three processes. That is like the one corresponding to absorption, spontaneous emission, and stimulated emission, right? We arrive at an expression for U, right? For U, and recall what is U. U was the same thing, right? U was the same thing, the same energy density that we obtained from black body radiation. Okay, right? Please note this. Okay, so in the next class, we're going to develop further. We're going to use this idea U further, and we'll make further connections between the different Einstein coefficients, which is going to be extremely relevant to understand spectral intensities, which in turn is connected with astrochemistry. All right. On that note, I end this lecture. Thank you so much.